Picture total darkness. Not the darkness of a closed room or a moonless night, but the absolute crushing black of the ocean at 600 meters down. No light has touched this water in millennia. The pressure here would collapse your lungs in seconds. And yet something is moving. Something enormous. You can't see it. You can only sense the displacement. A mass the size of a school bus, gliding with impossible silence through water cold enough to stop your heart. It has eyes the size of dinner plates, built to detect the faintest ghost of bioluminescent light. It has arms lined with teeth. It has been down here, evolving, for millions of years. And here's the thing that should unsettle you. There isn't just one creature like this. There are two, and they have absolutely nothing to do with each other. So why do they look the same? Two separate evolutionary lineages, two completely independent paths through deep time. And both of them arrived at the same answer. Become enormous, develop long predatory arms, hunt in the dark. The giant squid and the colossal squid share a common ancestor so distant it was barely more than a simple mollusk. Their family trees diverged hundreds of millions of years ago. Since then, they evolved on opposite sides of the planet, in different temperature ranges, under different pressures, facing different predators. They never shared an environment. They never competed. They had no reason to resemble each other. And yet, here we are, two animals that look, at first glance, almost like siblings. That's not coincidence. That's not accident. Something in the mathematics of the deep ocean keeps producing the same blueprint. The question is, why? And answering that question pulls back a curtain on how evolution actually works at its most fundamental level. The giant squid, Architeuthis dux, is built like a weapon. Its mantle alone can reach 2 meters. Add the two elongated feeding tentacles, and the total length stretches past 13 meters in mature females. It's fast. Hydrodynamically, it's almost perfect. A tapered, muscular body that pulses through the water using jet propulsion, capable of sudden, explosive bursts. Its suckers are ringed with sharp chitin, like tiny serrated crowns. Its beak, hidden at the center of its arms, can sever flesh with mechanical precision. For a long time, humans knew it almost entirely from the scars it left on sperm whales. Circular wounds, raised in white, pressed into the whale's skin like stamps. We didn't capture a giant squid on camera in its natural habitat until 2004. Before that, it was almost mythological. Even now, its behavior in the wild remains largely unknown. It hunts, it moves fast, and it almost never gets caught. Then there's the colossal squid, Mesonychoteuthis hamiltoni, and it is something else entirely. Where the giant squid is long and sleek, the colossal squid is massive, truly massive. It doesn't hold the length record, but it holds the weight record, up to 700 kilograms of dense, cold-adapted muscle and tissue. It lives in the southern ocean surrounding Antarctica, in water that hovers near freezing. Its hooks, not just suckers, but rotating, swiveling hooks embedded in its tentacles, can lock into prey and not let go. It moves slower than its northern counterpart. It doesn't need speed. It relies on ambush, endurance, and brute retention. The two squids are built around completely different philosophies of predation. One is a sprinter, one is a trap. Same basic architecture, opposite strategies. And somehow both of them ended up as the largest invertebrates on Earth. That demands an explanation. The explanation has a name: convergent evolution. It's what happens when unrelated species, facing similar environmental pressures, independently develop similar traits. The logic is almost mathematical. If a problem stays constant long enough, evolution will find the same solution repeatedly. Wings evolved independently in birds, bats, and insects. Eyes evolved independently in vertebrates and mollusks. The camera-style eye of an octopus and the camera-style eye of a human share no common blueprint. They emerge separately, shaped by the same physical rules of light and optics. Convergent evolution doesn't require communication between species. It doesn't require shared DNA. It just requires the same problem. And in environments defined by extreme conditions, deep cold, crushing pressure, perpetual darkness, the problems tend to be universal. Gigantism, it turns out, is one of evolution's favorite solutions. Not just in squids. Across the tree of life, wherever the conditions align, large bodies keep getting invented from scratch. But the conditions that drove these two squids toward gigantism aren't identical, and that distinction matters. The giant squid lives in the mesopelagic and bathypelagic zones of temperate and tropical oceans. Deep, yes, but not polar. The colossal squid lives in one of the most thermally extreme marine environments on the planet. In cold water, metabolic processes slow. Gigantism in polar environments, sometimes called polar gigantism, is partly a byproduct of this. Slower development, longer lifespan, more time to accumulate mass. Antarctic amphipods, sea spiders, and isopods all follow the same pattern. Cold water also holds more dissolved oxygen, which can support larger body sizes. For the giant squid, different pressures applied: depth, predation, competition in the open ocean. Two separate environmental equations, two separate survival strategies. And somehow the output in both cases included enormous tentacled bodies built for deep-sea predation. The ocean kept asking the same question in two different languages. Evolution gave the same answer twice. And then there are the sperm whales. If you want to understand why these squids grew so large, you have to understand the animal that hunts them. Sperm whales, Physeter macrocephalus, are the largest toothed predators on Earth. They dive beyond 2,000 meters. They hunt in absolute darkness, using echolocation so powerful it may stun prey on contact. They eat giant squid. We know this because their stomachs have been found full of squid beaks, and their skin is covered in the circular scars of squid suckers and hooks. This is an arms race in the most literal evolutionary sense. As whales became better hunters, squids that survived were the ones that grew faster, fought harder, dove deeper. As squids became more dangerous, whales evolved better echolocation, stronger jaws, more endurance. Each species drove the other forward. The deep ocean became an arena of escalation. And in that arena, being large wasn't just advantageous, it became the price of survival. But escalation under different pressures produces different fighters. The giant squid is a hunter built for open water. Agile, reactive, fast. Its jet propulsion system gives it sudden acceleration. It needs to chase prey and escape predators in three-dimensional space with no cover. Speed is survival. The colossal squid, by contrast, operates in the dense, cold water of the Antarctic deep, where ambush is more efficient than pursuit. Its hooks are designed for grip, not just contact. Its body is built for retention, holding on, not running. Think of it this way. The giant squid is a sprinting predator, lean and explosive. The colossal squid is a siege weapon, patient and inescapable. Same evolutionary category, completely different combat philosophies. And this distinction reveals something important. Convergent evolution doesn't produce exact copies. It produces variations on a theme. The ocean needed a massive, tentacled, deep-sea predator. It built two. But it built them differently because the ocean itself is not one place. Which raises a question that legitimate marine biologists have begun to take seriously. Could it happen again? Could a third giant evolve? The conditions aren't impossible. The deep ocean is still largely unexplored. We have better maps of the surface of Mars than of the ocean floor. There are environments down there we've barely sampled. If the pressures are right, sustained predation, thermal extremity, evolutionary time, gigantism could emerge again. There are already candidates, certain deep-sea octopus lineages, certain cephalopod species in intermediate size ranges that haven't stopped growing. Evolution doesn't pause. It doesn't finish. It runs constantly on every living population on Earth. And the deep ocean is one of the few places where the pace of human interference hasn't yet overridden the pace of natural selection. The blueprint exists. The pressures exist. The ocean is patient. Whether something is already down there, growing slowly in the dark, assembling itself toward a threshold we haven't witnessed yet, that remains an open question. Here is what the story of these two giants ultimately reveals. Evolution has no intention, no goal, no preference. It is a blind process driven entirely by survival and reproduction, operating across timescales that make human history look like an afternoon. And yet, it keeps building the same things. It keeps arriving at the same shapes, the same strategies, the same solutions. Not because it's aiming at them, but because the universe has rules. Physics has rules. Ecology has rules. And when you apply those rules consistently over millions of years, across independent lineages on opposite ends of the planet, you get the same answer. Two giants, built separately, shaped identically, hunting in the dark. That's not coincidence. That's not design. That's something stranger and more profound than either. That's a universe with structures so deep that life, left alone long enough, cannot help but find it. Evolution didn't build the same ocean giant twice. The ocean did. Evolution just followed the logic of the world.